Last lecture, we have seen the basic study of signals. Uh, what are signals? What are its examples? As well as we have learned how you can use these signals, how you can form, how you can see the expression, mathematical expressions of the signal, as well as we have seen one-dimensional examples of one-dimensional, dimensional, and multi-dimensional signals. Also, I have shown you the multiple waveforms of the signal. Okay. Now, in terms of communication engineering, you can see the continuous time signals are coming in. Generally, these continuous time signals you have utilized for the modulation as well as demodulation. Okay. Now, here we are dealing with the discrete time signal. So, question arises here: how you can achieve this discrete time signal? Okay, for that, to obtain that discrete time signal, here we need to convert the continuous time signal into the discrete time signal. Okay, so what will be the process of conversion of continuous time signal into the discrete time signal? So here we go through it one by one. Okay, here the sampling is the process that will help you to convert the continuous time signal into the discrete time signals. Now here our lecture is dealing with the sampling theorem. What is the sampling theorem, and what are the methods in the what will be the way of conversion of the continuous time signal into the sampling into the discrete time signals. Okay. Now, yesterday we go through this basic theorem. Okay, this theorem states that a continuous time signal can be represented in its samples and can be recovered back when sampling frequency fs is greater than or equal to the twice the highest frequency component of message signal. Okay, now here the message signal is represented as fm. Okay, and the sampling frequency is represented as fm. Okay, so here the condition is that fs should be greater than or equal to twice fm. Okay, then and only then you can say the sampled signal will be achieved, or you will get the discrete time signals. Okay, now in this lecture we will understand what do you mean by sampling and what is the sampling theorem. Now it's time to move on to discrete time signal, but wait, why we are required to study the concept related to the discrete time signal? When we have continuous time signal, the answer is extensive use of digital technologies nowadays. So if you look around yourself, you will find there are so many digital technologies in implementations. But we know all real-time signals are analog in nature, or you can say all real-time signals are continuous in nature. So they are continuous time signal. So the information is carried by continuous time signal, but the system we are using our digital in nature. Therefore, they will not process continuous time signal, and it becomes important to convert continuous time signal to discrete time signal. And this process of conversion of conversion, or you can say reduction of continuous time signal to discrete time signal is known as sampling. Now let us define sampling property. Okay, so here sampling is the process of reduction of continuous time signal to a discrete time signal. And if you want to get continuous time signal back from the discrete time signal, then you can do this, but there is some condition, and now we will try to obtain the particular condition. So let's move on to the next part of this lecture. Okay, you can see some waveform are shown in the slides. Okay, here I have given you a proof. Consider a continuous time signal x of t. In the left side corner, you can able to see x of t signal. Okay, a sinusoidal wave is varied with respect to time. The spectrum of x of t is band limited to fm in hertz. That is, the spectrum of x of t is 0 for omega greater than omega m. Now, sampling of input signal x of t can be obtained by multiplying x of t with impulse and impulse train delta t of period ts. The output of multiplier is a discrete signal called sampled signal, which is represented by y of t. Okay. Now here, to prove this continuous time signal into the discrete time signal, here we consider the continuous time signal along with a impulse train signal, that is delta t. Okay, now here now here we represent the continuous time signal by x of t and representing it by x of t, because this signal is known as message signal. This is known as message signal because this signal is carrying the information. Now we want to process this message signal, and you must note one point here. This signal we have taken is a band limited signal. We are assuming that we have taken a continuous time signal which is band limited. Now, why we are taking a band limited signal and what is band limited signal? I will explain now. Band limited signal means its Fourier transform, or you can say the spectrum of the signal will be non-zero only within a small range of frequencies. For example, let's say this signal is having Fourier transform x of omega. That x of omega is shown bottom side of x of t. Okay, a triangular wave is shown, and right hand side it is written omega m, and left hand side it is written minus omega m. Omega m is nothing but a maximum frequency component. This is the maximum frequency component of x of t. Okay, now here this Fourier transform x of omega like this. Okay, now you can see that the Fourier transform or spectrum is non-zero, and is non-zero from minus omega m to plus omega m. So here in this case we are having the spectrum which is non-zero only for finite range of frequency, and it will be helpful when we will try to extract the continuous time signal from the converted discrete time signal, and this point will be more clear after some time. So far now just understand that we are having a continuous time signal carrying the message. Okay, so x of t is a signal, this signal is carrying, this is a continuous time signal, okay, and it carries a message. Okay, and his Fourier transform is like this, and the Fourier transform is non-zero between minus omega m to omega m. And also note down that here what is omega m? Omega m is a maximum frequency component of message signal x of t. Okay, now omega m will be used a lot in this course. Okay, so remember what it is. It is the maximum frequency component of x of t. If x of t is having multiple frequency component, then maximum frequency out of those frequency component is omega m. To feed this continuous time signal to a device known as sampler, or you can say a multiplier. Okay, now here a multiplier is shown. One side there is x of t as an input, and another side there is another signal, that is delta of t. Okay, so here it is acting as a multiplier, and multiplier means it is going to multiply two continuous time signals. First signal is x of t and second signal is delta of t, and you can clearly see that delta of t is a periodic impulse train, and this periodic impulse train is having the fundamental time period equal to ts. Okay, so here delta t is represented on y-axis and t is represented on x-axis, and here a train, a pulse of train is represented. Okay, so each point is marked as a ts, twice ts, thrice ts, or in left hand side minus ts, minus 2ts, minus 3ts. Okay, so that's why it is called as an pulse train. Okay, so here ts is a fundamental time period, or it is sampling period. It is also called as sampling period. Okay, or also known as sampling interval. Okay, it is also known as sampling interval, and we know omega s, we know omega s. Okay, now here omega s means here it's is Fourier transform. Okay, so omega s, which is regular, which is angular frequency, is equal to 2 pi divided by ts, and omega s is known as sampling frequency, is known as sampling frequency. Okay, so now we have two frequencies. First frequency is omega m, is known as maximum frequency component of x of t, and the another signal is omega s, which is sampling frequency or angular frequency of the periodic impulse train. Okay, and remember both frequencies, because we are going to get relation between these two frequencies only, as we are having periodic impulse train like this. We can write delta of t is equal to summation of n is equal to minus infinity to infinity delta of t minus n ts. Okay, I clarify this expression in the next one PPT. Okay, here you can see delta of t is written. Okay, if you take the trigonometric Fourier series representation, okay, you will get delta of t. Okay, now I elaborate this expression, that is delta of t is equal to summation of n is equal to minus infinity to infinity delta of t minus n ts. Now if you elaborate it, you will find the expression number 2, that is delta of t is equal to a0 plus summation of n is equal to 1 to infinity in bracket an cos of n omega s t plus bn sin n omega s t. Okay, we mark it as an expression number 2. Now as this summation is showing you here, okay, uh, now here n is equal to 0. From this expression here n is equal to 1 to infinity. Okay, now you have a delta terms. Okay, delta t terms. Okay, uh, now if you sampled, if you find sampled signal, that is y of t is, it is a mixture of x of t and delta of t. So it is represented by expression 1, that is x of t into delta of t. Okay, we will have resultant waveform like this. Okay, in this way, okay, here I show you the waveform. You will get a resultant waveform, that is y of t. Okay, that y of t is a resultant waveform. Okay, okay, this is, okay, this waveform we are having different impulse, and the area or weight of the impulse is equal to the instantaneous value of signals. Okay, for example, if you talk about the impulse present at Ts, then the impulse will have the weight or strength equal to instantaneous value of x of t. This means when t is equal to Ts, the value of x of t will be the strength or weight of particular impulse, and in this way we have a new signal which is known as sampled signal, and it is represented by y of t. Okay, y of t is equal to x of t is multiplied with a periodic impulse strength delta of t, and now we are interested in obtaining the spectrum of the sampled signal. This means we are having y of t and we want to have its Fourier transform as omega of still, and we also know that y of t is equal to message signal is multiplied with periodic signal delta of t. Okay, now here how you will find Fourier transform signal. Okay, so for that here we first find the value of a0, a1, an and bn. Okay, here a0 is 1 upon ts integration of minus t by 2 to t by 2 delta t into dt. Okay, if you solve it, you will get of 0, okay, and after that if you put value of delta 0 is nothing but 1, okay. So that's why if you put delta 0 is equal to 1, you will get 1 by ts. Similarly, second, an is, its expression is 2 upon ts integral of minus t by 2 to t by 2 delta t cos n omega s delta t. Okay, if you solve it, you will get 2 upon 3 by 2 delta 0 cos n omega 0 cos n omega s into 0. Okay, so cos 0 is nothing but 1, delta 0 is nothing but 1. Okay, you will get 2 upon t s. Okay, then bn is 2 upon ts. Here it is integral of minus t by 2 to t by 2 delta t sin n omega s t delta t. If you solve it, here sin n omega s into 0, sin 0 term will be 0. So that's why here the whole term will become 0 and you will get bn is equal to 0. Now, if you substitute all these values in expression 2, you will get delta t. Okay, that delta t will be looks like this. Delta t is equal to 1 upon ts plus summation of n is equal to 1 to infinity in bracket 2 upon ts cos n omega s into t plus 0. Okay, now if you put this whole term into expression 1, you will get y of t is equal to x of t into delta t. Now we put all these terms in your expression 1, that is x of t is multiplied with the delta t, that is 1 upon ts plus summation of n is equal to 1 to infinity cos of n omega s into t, and out of the bracket x of t will be there. Now we take x of t common from both term, so you can find x of t will be out of bracket, that is equal to x of t in bracket 1 upon ts plus summation of n is equal to 1 to infinity in bracket 2 upon ts cos n omega s into t. Got it? Now if you solve it again, you will get 1 upon ts in bracket x of t plus 2 summation n is equal to 1 to infinity cos n omega s t out of bracket x of t. Okay, now finally if you expand the summation term, you will get y of t is equal to 1 upon ts x of t plus, see the expanded term, 2 cos omega s t into x of t plus 2 cos 2 omega s t into x of t plus 2 cos 3 omega s t into x of t dash 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 up to infinity. Okay, so that's why you can find this will be the resultant term. Now we take Fourier transform on both sides. You will get y of w is equal to 1 upon ts in bracket x of w plus x of w minus ws, w is nothing but omega, okay, plus x of omega plus omega s plus x of omega minus 2 omega s plus x of omega plus 2 omega s plus dash dash dash. Okay, so here if you take all these terms, okay, you can find y of w is equal to 1 upon ts summation of n is equal to minus infinity to infinity x of omega minus n omega s. Okay, here the value of n is varying from 0 plus minus 1 plus minus 2 dash dash dash. Now if you put the value of n in this expression, you will get the earlier expression. Okay, now here you can find total 3 graphs shown here. Okay, first graph is showing here fs is greater than twice fm. Okay, here it is oversampling. Okay, here it shows a oversampling, and this is the condition of our sampling. Okay, to obtain the discrete time signal. Okay, now if fs is greater than or equal to twice fm, then you can find the sampling signal. Okay, but in case if this condition is not achieved, you can find the slightly perfect sample signal, that is fs is equal to twice fm. Okay, then here the signal will be looks like this, and if the fs is less than twice fm, then you can find undersampled signal. Okay, the undersampled signal are overlap with each other. Okay, due to that overlap, here the aliasing effect will be generated. Okay, so that's why this aliasing effect, this is the crossover. Okay, crossover means here the signals are superimposed with each other. Okay, so to obtain the perfect sampling, or oversampling or pure sampling, okay, you can say. Okay, so you, what will be the condition of sampling? It will be fs should be greater than twice fm. Okay, now this is about the sampling theorem. Okay, from this you can find, you will get a discrete time signal. Okay, so the resultant discrete time signal will be achieved as a y of t. Okay, you can find these are the discrete time signal, that is resulted discrete time signal. Okay, now this is about the sampling theorem. Now in the next lecture we continue with the discrete time signal basics. Okay, so I stop here.